Yeah, I'm gonna do a video about modal logic. And let's see, it's the Windows shared out the drawing. Uh-huh. Okay, I think this is good enough. All right, modal logic. Um, it's a really, really interesting way of doing logic where the facts can change as long as you have a state machine, and that basically means code. So I got this animal with me, and if we want to model the behavior, so let's say she is in state asleep. So so and if we think of this as a bunch of variables, say so not only is she in state asleep, um she might be thirsty, and it's zero right now, hungry, zero. Okay. And if we want to reassign a variable, like as in code, we want this graph to actually be code. So if we want to change hungry from 0 to 1, there's actually going to have to be a state transition for this. So H, so let's call it H prime actually. So the new value of H is going to be 1 when we go into next state. Okay. And as the day goes on, she may get a little more hungry. H prime equals H plus 1, or she might get a little less hungry. H prime equals H minus 1. And because this is a Markov chain, there are probabilities associated with this. So she might be asleep like 0.9% of the time, but she will wake up and want to do stuff for the rest of the time, 0.1% of the time, right? So if we start in the state in these variables, asleep. In fact, let's call that variable W for like wake. Just wake equals 0, right? So she's not awake. Okay. And she gets hungry. And then when she gets hungry, uh, in a state where she gets more hungry, and when we enter the state, we're also saying awake. So W equals 1. So we change two variables. So we change H and 1, assign new values to it. So all the arrows coming out of the first state add up to 1, which means that as a Markov chain, it's complete. So in this case, we'll say she can get more hungry or maybe less hungry, right? So we'll say that this has a probability of 0.2, and this has a probability of 0.8. So they add up to 1. Um, so we haven't done any other variable alterations. So we could have a trace where it start off with W equals 0, T equals 0, and H equals 0. And there is a Markov state transition. Most of the times it just goes to 0.9 and nothing happens, but something happens in them, and suddenly we got H is now equal to 1 and W is equal to 1. And if it happens again, it'll be H, um, uh, say more hunger or less hunger, right? So H is now equal to 2, because we took this 0.2% probability of taking the state, right? So now she's at hunger level 2, and thirsty is 0, and she's awake, right? So that was a change. That was a change. So we started off here, and variables change here, and then she's in the state where she gets more or less hungry, right? Um, And so let's say that it's only 0.1, but she goes to a state where she's being fed. And so hunger goes up to 2, and then say when she gets thirsty, T plus 1. The animal is now at hunger level 2, and now also thirst level equal 2. And say this wakes her up. So oh, she is awake, right? So let's say that she's getting food. And so when getting food, hunger goes H prime equals H minus 1, right? And actually, just to be kind of consistent, let's just make it where she gets more thirsty, thirsty increases. Right. So hunger equals 2, and then there could be a transition off to this other state. So you can always see what the variables are going to be. So if we were to write a temporal logic state to say eventually, hunger goes to 0, right? So it would be H equals 0. And how does that happen? Um, State A, B, C. There would be a path where it starts off in state A, right? And then she goes into B, where she could get hungry for a while and also thirsty. And then she goes into C, where she's being fed and her hunger goes down and her thirst goes down. T minus 1, right? And then when it reaches a state where T equals 0, we're done. We're done giving her drink. And if she goes to state H equals 0, she's no longer hungry, right? So this state machine allows us to use these modal logic things. So eventually hunger goes to 0, right? In a way that we write it in the math would be like a diamond. So diamond H equals 0. And that means that when she's in the initial state A, and then she goes through B a couple times, and her hunger goes up, and her thirst goes up, and then she eventually goes into state C, where she's getting something to drink. And also we could add in where she gets something to eat, right? So H prime equals H minus 1, right? And so if H is equal to 0, then we make a change to the variable, and thirst goes down, right? So when thirst is 0, no more thirst for now. So now let's talk about what modal operators are. You have to have a state machine in order for it to work, because there's like if you make a statement that says for all paths in a state machine, say we do this for all in the state machine, eventually in the future, right? So it's a diamond in the future. So for all paths in the future, it means eventually, and it means unavoidably and eventually. For all states in the future, because we have these Markov chains, you could sit here and do nothing. You could go wander off and do some other things. So the only thing that really would stay the same is if we had a variable that never changed. So there's nothing that we could put in here unless a new variable, right? If a different variable was like say b equals 0, and it would be equals 0 on the start, that variable never changes. But if we say possibly, say there exists a path in the future, so in the future, possibly, so that this would basically be called like EF in a project. So eventually, possibly, she gets fed, which means that say the hunger is greater than 0 implies that, let's see, eventually it's possible that she'll be fed. So then H equals 0. And we'll do that. And we'll just say for all paths. So what we're saying is we know that she will eventually get hungry, and when she eventually gets hungry, not to worry because she will possibly be fed, right? And we could actually make this more strong and say that she will. Well, it always happens. It always happens that when she is hungry, she gets fed. Okay, so let us make a new state machine, kind of clear this stuff up. So the the temporal logic operators, got a bunch of them, and one of the books I'm reading through. Buggy, all right. This is one of the books I'm reading through. I wonder if it's rendering backwards or not. Probably is. But it's a temporal logic and state system. And one of the things that drove me nuts about trying to figure out what's going on in Kripke systems is they start drawing all these diagrams like this state goes to this state, and you go into it, you go back out of it, and what you can say is if I am in a particular state, then I can like start to make statements about it and say from that state, what you can do is you can say, well, it's possible from this state to reach this state, right? And what that means is there is a path that you could choose, and say that we just name it A, B, so we can have some sentences. So a possible path to reach E is B, C, B, C, E, right? And so since we actually reach that path, uh, it is possible, say, possibly in the future there exists a path. But in CTL, we write this a little easier. We use like regular letters. And so this would be abbreviated as E F, right? So we'll say it's in the future. It's a modal in the future. So we would say something like EF to say possibly. So possibly we reach state state E, right? So we possibly reach state E. And what that means is if we want a proof of it, we say BCBCE to show that we reached it, right? And the reason why it's possibly is because it uses this eventually. There exists a future where we are in E. That means that if you were going through the state machine, trying all the different ways of going through it, not all paths would lead to it, but what we could do is we could find one path that leads to it, right? So we go this way, find something that reaches like state E from state B, right? So from state B, we can reach state E possibly. What it means is not all choices are going to get us there, but there exists one. So that would be E, F. So it means there exists in the future, right? So in the future, F basically means eventually. It means unavoidably, right? And there is always is its dual. Yeah, always is the dual of eventually, but it's a little bit tricky where if you want to include possibly, it's uh it's really a form of optional eventually, right? Because eventually means it's definitely going to happen. Like if you fly around in a plane forever, you're eventually going to come out of the sky because you ran out of fuel, right? But possibly means you might go a shorter distance than completely running out of fuel. You can actually get from one place to another without running out of fuel as long as you time it right, right? And so possibly and necessarily. And what necessarily means is that if you follow in this state machine, you will never reach a different value, right? So say that in all of these things, there is a variable, like say it's x is equal to 3, and it happens to be that x is equal to 3 in every single state. It's never reassigned a different value. And this happens with the sort of things that are like factual and the facts never change. For instance, if you say that we have a bunch of probabilities and they must all sum to 1, you could have code that changes them. You could have like 0.2 plus 0.8, and you could, and the code could end up splitting it up to one variable is 0.1, another one is 0.1, and this is the plus 0.8, and it always happens to add to 1.0, right? That could be like some proposition. It would be a statement that is true in every single state, and that means the necessary state. So that's like necessarily. So see necessarily some proposition, right? And something that is necessary is like an inverse of something that happens to be possibly, right? So if I say, for instance, it is not uh, is not impossible that, right? That way. So if P is not possible, not P. So if we can always find a P that is false somewhere, um, then that is the same thing as saying it can't be true everywhere, right? So if if P being false is false, it's basically it's not like not impossible. It's not impossible, right? And you can go the other way with these, where if you have something that is possibly true, Q, in which you have is two ways of writing not. You have something that is always true, but you negate it. So Q always being false never happens, which means it's possible. That means possibly, right? Um, And if you think about it, this really isn't like a time modal, but we interpret it in such a way to where the facts only change on a time step. So you got to go from B here to C, which is a time step for any fact in the world to change. So that allows us to combine eventually with possibly. And one of the really cool things that it allows us to mix together modalities. Um, And so let's say we have for all something happens in the future, like it happens at least once. And what it means is there's past and you can't get around it happening because it always is going to happen somewhere. Like it happens here, here. You try to evade it, but on some path there's always a way where it happens at some point in the future, right? And that would be different from for all globally, which means from, say it's from this state here, that would mean that once that value is set, it's never going to be something else. And this typically would happen like on an implication, like if the landing gear light is on, then that implies that landing gear is down. right? You shouldn't have a situation where it tells you that the landing gear is down, but it's actually not. Um, so that's what for all globally means. So this one is eventually, it's inevitable. It means you can't get around it. Um, but if you were to say instead of AF, you were to say EF, what you're saying is it's possible. And what that means is you got a tree, and there is some path that you can take where that thing happens, and it might only be in one place, right? It means it could happen. It may fail to happen, but there may be, there may be multiple ways for it to happen. And EG is a little stranger. It's kind of like can always. Um, which means that it's not inevitable, but you can definitely find a path where it's always true. But this is like you can fly without crashing the plane, right? Of course, there are many places that you can go to where you do crash the plane, right? So, so that's e.g., eventually, always in the future from the state, right? And here would be eventually in the future just for some state, right? So there exists a future state, EF. That's what that means. And this, if you look at it, is for all tasks, you will run into G. And the other one is not yet stated that necessarily and always. It basically means that it's just true everywhere. And the example that they like to use in philosophy is to say like a fact that can never change because of like the nature of what it is. Like for instance, if you have a E is equal to 1 plus 1 equals 2, there is no state where 1 plus 1 is not equal to 2. And a place where you use these kinds of things in practice is you'll have like a P implies Q. And if it's something sensible, then it's necessarily true. And it would be like if the light bulb is burnt out, it will not light up. Um, but you could have a P and a Q that are nonsensical, where it says something like, P would be if the light is not on, the engine won't start, right? And burnt out light bulbs don't cause engines to not start. At least the way that most things are designed. In any case, the reason why I'm so interested in modal logic is that you end up in a situation where you can define a software system as a set of communicating Markov chains. And what I mean by that is there's probabilities on things, so, and they all add up to 1 going out of a state. So that's 0.5, 0.5, and they could be different ways of assigning variables when they do that. So as long as 0.8 here, and then maybe 0.2 here, right? So it totals 1 coming out, and you have to land somewhere. But in case that's a Markov chain. And what that means is you can represent it as a matrix, where A goes to B, B goes to C, and there's a probability associated with it. And if you take that square matrix, you exponentiate it really high power, it will give you the probability of being in each state. That's like a thing for like how Google PageRank works, right? It's like they throw you in a world where there's like random web pages and they all have links to each other. And if you were to follow the web pages infinitely, useless pages, you would only be in them a tiny fraction of time, and you've got very, very high traffic pages with like a high probability that you're at that page. But in any case, you can have a software system that represents one object, like say this is like a bakery. So there's like a finite state machine with some code, and then there is a truck that simulates deliveries, and when things happen, um, there's a truck. And then there is a storefront, which is also a state machine. And it's got a whole bunch of complex states, and it's enough that you could like write software about it. So if you have a bunch of variables and you start assigning them values, then you end up with a situation where the code has determined what these state machines must be, right? So if I assign X to be X minus one, then it goes into another state. But the thing is, if you have these Markov chains and you assign them random probabilities, that allows you to do simulations. But what's really beautiful is if when you make a transition, you cause a message send from one channel to another. And let's say that I'm trying to think of a nicer way of doing this. Say that there is a channel that's shared between them, and during this transition, we drop a message in the box. If it, and if it's full, we have to wait until we write it in the box. And then, and if the truck is reading from that variable, and he gets to that point where he reaches a state, he has to stop and wait for it. So what would happen is the bakery delivery gets to this state, and if the truck hasn't arrived yet, when it does arrive, the message will go through, and then it'll be in this state, and then the state machine will go forward. So if we have all these state machines that are sending each other messages, then you can represent a software process like this. And the beauty of it is you're trying to figure out, like, is it always possible? So always in the future, um, can we get bread? So got right. And the reasoning behind this would be is you would start off the state machines, and you would have to like walk through the machine until some bread gets made in the bakery, and then they load the bread onto the truck, and then the truck arrives at the store. And so some of the bread that got made at the bakery ends up going through the truck and into the store. And the idea is you want to keep on counters. You want to say, I got 5 loaves of challah now, and I got some live bread and whatever. And then you would have other processes like customers that model people coming into the store and running off with some of the bread in exchange for uh, some cash, right? And so if you model the bakery making, like a list of all the stuff that they made, and then going to the driver, it causes messages to get passed, and then at the store, you're in a square terminal, and people buy the bread in exchange for loaves. And what happened at the end of the day, you got a bunch of loaves that were not sold, and you have to count them. And so this software system basically becomes like a modelable. Normally, formal methods are used to solve really, really, really hard problems that nobody cares about. And I am trying to make something that is a large language model, takes your English statements, generates a state machine that's required for the modal logic to work, and then you apply modal logic for like the proofs that certain things happen. And if you do it that way, then you have a way to specify like real business applications, and pieces of software. I don't want another product to do like bit flipping protocol, or even something that's kind of useful, like multi-patchless and whatnot. Of course, you want certain parts of it to be that, but the idea is I want to make a requirements file that I can check into the repository. It's machine processable. You can verify that like all the modal logic things, like yes, we can get bread. It might tell you, oh, you can't get bread by noon because the guys come in at 5, and then by the time they're making the bread, it's on the delivery truck at 1, and by then you've already two-hours your customer to get angry because there's no bread yet. That actually happened when I was in a store. But in any case, that's what this whole CTL project in my GitHub is all about. And I discovered I got a little bit of a problem that I didn't think too hard about message passing. So I need to be able to not just one state machine that has probabilities, but I need multiple state machines with probabilities. Which means that when I make these state machines, I need a way to merge them together into a bigger state machine so that I can like prove that certain things happen, right? Like I merge the truck and the store together, and I find some state where like bread deliveries like don't happen, or I find a proof that no matter what you do, bread's going to get delivered. According to the finite state machine that we use to model the world. But in any case, I'm done with this. I got this guinea pig. Um, See you next time. Stop this buggy.